Good day and welcome to the Moscow Telecommunication Seminar. Our today's speaker is Viktor Torgunakov. Viktor received the bachelor degree in applied mathematics and physics from Moscow Institute of Physics and Technology this year. Currently, he is a master student at the MIPT and an intern with the Institute for Information Transmission Problems. Today, he will tell us about new amendment to the Wi-Fi standard aimed at V2X scenarios. Victor, the floor is yours.
Good evening, my name is Viktor, and today I'm going to tell you about channel bonding techniques in IEEE 802.11bd networks. Firstly, I would like to give a brief introduction. Nowadays, intelligent transport systems are actively developing, and it's expected that their deployment will improve road safety and boost driving comfort due to, for instance, applications that anticipatorily alert driver about a road accident, a maneuver of a neighboring vehicle, or a sudden appearance of a pedestrian. It's expected that in the future, intelligent transport systems will provide fully autonomous vehicles. However, it's impossible to deploy full-fledged intelligent transport systems without creating underlying vehicle-to-everything networks, which allow cars to exchange information with each other, vehicle to vehicle, with objects of road infrastructure or roadside units, vehicle to infrastructure, with pedestrians, vehicle to pedestrian, and with cloud infrastructure, vehicle to network. Nowadays, the most widely deployed technology for vehicle networks is dedicated short-range communications that is based on the set of standards for wireless access in vehicle environment. The crucial part of this technology is medium access and physical layers. And these layers are specified by the IEEE 802.11bd standards. And today's talk will be devoted to these standards and to its amendments 11bd standard. So now let me briefly outline the plan of my talk. Firstly, I would like to tell you about main features of the 11bd standards. Then I will explain why the need for evolution from the 11bd standards to 11bd standard has emerged. Thereafter, I will describe main novelties of the 11bd standard. After that, I will give a more detailed review of one of the features of the 11bd standards about the channel bonding techniques. And at the end of my talk, I will provide a comparative analysis of channel bonding techniques that can be used in 11bd networks. Okay, let's move to the features of the 11bd standard. This standard was approved in 2010, and it is based on the legacy 11A standards that was developed for Wi-Fi networks. The main goal of the 11bd standards is to provide vehicle-to-vehicle and vehicle-to-infrastructure communications. So the communications in fast-varying vehicle environments, but not only provide them, but provide them with minimum changes in 11A physical layer. Okay, the main features of the 11P physical layer is the usage of narrow channels and operation in the 5.9 GHz frequency bands. So 11P devices use 10 MHz channels instead of 20 MHz channels used in 11A networks. But they not only use narrow channels, but all timing parameters are scaled with a factor of 2, as you can see from the table, maybe apart from the slot time. This scaling was introduced because not 0.8 microseconds gap interval used in conventional Wi-Fi networks isn't long enough to deal with anti-symbol interference in vehicle networks. Okay, another feature is the operation in the 5.9 GHz frequency bands. It allows to prevent interference from Wi-Fi devices, LTE devices, and from other technologies. The main medium access layer novelty of the 11bd standards is the operations outside the context of basic service set. I would like first I would like to remind you some facts about the independent basic service sets used in legacy Wi-Fi ad hoc networks. If a station wants to connect to ad hoc Wi-Fi network, it should connect to an appropriate independent basic service sets. And this connection implies authentication and association procedures to provide data security and exchange parameters for subsequent data transmissions. However, these procedures can take seconds, which is excessively long in vehicle-to-everything networks where all connections should be established in short time frames. For instance, in the situation when two cars approach to each other. Thus, the 11p standard introduced the operations outside the context of basic service set that doesn't require authentication, doesn't require association, and stations can exchange data immediately. So 11p station can either connect to basic service sets or operate outside the context of basic service set. Okay, as for 11p networks deployments, they're deployed in most developed countries like the US, in such regions like the European Union, in Japan, and in some other regions. You can see the map with all the deployments of DCC networks in the US on the slide. And an example of such deployments, the California Connected Vehicles testbed, which consists of 31 intersections with traffic controllers. These controllers transmit so-called signal phase and timing and map messages. Signal phase and timing messages transmit carry information about the signal of a traffic lights, whereas map messages carry information about the geometry of the intersection. And vehicles that are equipped with DCC radio can obtain these messages and use them for some safety applications. Okay, now let's move to the phases of V2X networks deployment. It's expected that V2X networks will be deployed in three phases. The first phase implies implementing three main services. The first service is based on periodically broadcast messages that carry information about the position, the speed, the acceleration, and the size of the transmitting vehicle. The second service is based on event-driven messages that are transmitted due to some road events like road accidents and carry information about the location of these events, its class, and its severity. The third type of services relies on messages transmitted by roadside units. These messages can carry information about the geometry of intersection, a traffic light phase, and some other information. And SPAT and map messages that were mentioned on the last slides are examples of messages transmitted by roadside units. Typical requirements of the WAN applications are the latencies that allow more than 50 or 500 milliseconds. It depends on the application, and the packet loss ratio that is lower than 10%. These technologies are in this phase now. Okay, the main novelty of the day 2 phase is cooperative perception services, which allow cars to exchange data from sensors. Such sensors are LiDARs that use optical spectrum to detect objects nearby, ultrasonic sensors that use ultrasound radars that use obviously radio waves, cameras, and some other sensors. And the requirements of data applications are stricter than that of the WAN applications. For instance, so-called cooperative perception messages used for sensor data sharing require the packet loss ratio that is lower than 10% and latency that is lower than 10 milliseconds. And the most stringent requirement of the data application is the packet loss ratio that is lower than not 0.001%, and the latency is that's lower than 3 milliseconds. Okay, day 3 and beyond phases imply that vehicles are already highly automated and they can drive with minimum efforts from the driver's side. This phase also implies that vehicles can share planned trajectories, roads, maneuver intentions with other stations. And also that vulnerable road users, that is pedestrians, cyclists, motorcyclists, and others, are equipped with a radio that helps them to avoid risky situations by exchanging data with other stations. For instance, a vehicle can anticipatorily obtain information about a child that's crossing the road and stop. Studies show that 11p networks can provide day one safety applications if network traffic is moderate. However, 11p networks will unlikely ensure the work of day 2 and beyond applications. That's why IEEE 802.11 has established the 11bd task group that aims at developing a new standards that will provide advanced V2X services. The development of 11bd standard has been launched in November 2018, and the standard is expected to be approved by September 2022. Okay, now let's move to the main features of the 11bd standard. The 11bd standard aims at increasing throughput, improving reliability, and enlarging the transmission range. To achieve it, it introduces a set of features that can be supported by using a new frame format, a next generation of V2X, physical layer protocol data unit, or NGPDU. Let's look at PPDU formats in 11bd networks in more details. So the 11bd standards specifies two frame formats. The first one is non-NG PPDU, and the second one is NGV PPDU. The non-NG PPDU format was introduced for backward compatibility with 11p stations, and its format is exactly the same as the format of PPDUs in the 11A standards. So first there are legacy short and long tuning fields that are used for channel estimation and synchronization. Then legacy signal that is used that carry information about lengths of ongoing data and modulation encoding scheme of ongoing data. And and NGPPDU format was introduced for high performance of 11bd networks and to support its features. So the start of preamble is the same as in non-GPDUs. So 11p stations can detect it, but then there is a repeated legacy signal that is used to distinguish NGV and non-GPDUs transmitted by NGV vehicles. After that, there is 2 times repeated NGV signal that carry information about modulation encoding scheme of subsequent data and about features used by 11bd standard. Then there are NGV short tuning field and long tuning fields that are used for MIMO technology, which is one more feature of 11bd standard. Okay, the first two features of the 11bd standards is the usage of low density parity check codes and midambles. LDPC codes will be used instead of convolutional codes that we used in the legacy 11p standards, and they may give a prominent signal to noise ratio gains compared with convolutional codes. Okay, and only data blocks will be of NGPDUs will be encoded with LDPC codes, whereas legacy signal and NGV signal will be encoded with convolutional codes. Another feature is the usage of midambles that are simply NGV LTF signals inserted between several OFDM symbols. The allowed periods are 4, 8, and 16 OFDM symbols. And midambles were introduced because in vehicle environment, information for channel estimation obtained from the preamble quickly becomes obsolete, and midambles help to update it. Studies show that the joint usage of LTPC codes and midambles can give up to 2.5 dBm signal-to-noise ratio gain in the point-to-point scenario at the 5% packet error rate level. Okay, another feature of the 11bd standards is the usage of adaptive blind transmissions that are used to improve reliability in case of sporadic interference. And the 11bd standard allows to retransmit frames up to 3 times with a time gap of sieves between them. Moreover, both NGV and non-GPPDUs can be retransmitted. Naturally, the 11bd standard doesn't specify when to retransmit, so this decision is implementation dependent. But the station can make its decision based on, for instance, channel busy ratio. Okay, another feature of the 11bd standards is the usage of new modulation and coding schemes. The first new modulation is the MCS with 256 QAM. That may be used for bandwidth-hungry applications, such as some infotainment applications. Another new modulation is binary phase shift keying with dual carrier modulation, where data bits are repeated in 2 5 MHz channels. This modulation can improve reliability at high distances and also increase the transmission range. Other features of the 11bd standards is the usage of single user MIMA, maximum 2x2, and it can be used only for unicast transmissions and may provide bandwidth-hungry applications. One more feature is the operation in the 6 GHz frequency bands using the 11AY standard capabilities. So this operation can provide such applications as see-through applications that allow car to see, for instance, through a huge truck which is in front of it. And one more feature is the usage of channel bonding techniques. And I would like to elaborate more exactly on this feature. Okay. So there are some questions. On one of the previous slides, you said that independent basic service set requires authentication and association, but association is done with an access point. Did you mean infrastructure-based basic service set? Yes, maybe I was slightly wrong. I mean that so the connection establishment delays in both infrastructure-based service sets and independent-based service sets, they are too long. So both modes are available in vehicle territory networks, but usually operations outside the context of basic service sets are used. Okay, and Ilya Levitsky asks, following Dmitri's question, if there is no authentication, how security is provided? What if there is a malicious signal coming the roads? Do you have any information about it? Okay, to be frank, the security is a major problem in ad hoc VTX networks. The security implies much higher latencies. Okay, I'm sorry. This security management is out of scope of 11bd standards. It's provided by higher levels, by the level that is even higher than the transport layer. And when vehicle obtains a frame of other vehicle, if it knows nothing about it, it can send a request to roadside units and through the rotate units, it can connect to a credential system, and using the information obtained from the credential system, it can decide whether the digital sign of obtained message is right or not. But overall, security is a big problem in LLMBD networks because it's highly increases latencies. Okay, my pleasure, Ilya. Okay, so let's move to channel boolean techniques. To begin with, I would like to remind you how enhanced distributed channel access, which is a basic single channel access method used in 11BD networks, operates. If an ePPDU arrives in the empty queue of a station and the Bykov counter of a station has already expired, and the channel is idle for at least 8 ifs, the station can transmit the frame immediately without invoking the Bykov counter. Otherwise, if channel is busy and station successfully decodes the transmitted frame, it waits for ifs after the frame transmission, invokes the Bykov counter, and when it reaches 0, it transmits the PPDU. In turn, when a station fails to decode the transmitted frame and detects that the channel is busy because the energy in channel exceeds some threshold, energy detection thresholds, it waits for ifs, it is longer than ifs, and then invokes the Bykov counter. Okay, I would like to also remind you how the legacy channel bonding technique from the conventional 11A standard operates. The station that uses this technique should first select the primary channel. And the station performs the Bykov procedure only in the primary channel, and this procedure is similar to that of UDCA. So when the Bykov counter reaches 0, the station can either transmit in the primary channel or in 2 channels at once. The station transmits only in the primary channel if the secondary channel is idle for less than pifs. Otherwise, if it's idle for no less than pifs, it transmits the frame in 2 channels at once. Okay, this channel bonding technique wasn't included in the 11BD standards because it may be unfair to stations in the secondary channel because there is no Bykov procedure in the secondary channel. And appropriate work and road safety may depend on the appropriate work of all stations. That's why this fairness is crucial. The standard developers even consider the option where the station waits for ifs that is longer than pifs on the secondary channel. But finally, after some investigations, they decided not to include this channel bonding technique in the standard. Okay, now the 11BD standard specifies 2 channel bonding techniques. The first one is basic, whereas the second one is the extension to the first. The second name of basic channel bonding technique is the technique without fallback. The station that uses this channel bonding technique decrements the Bykov counter in 2 channels at once. So the Bykov counter is decremented when 2 channels are idle for a slot time. Before operation, the station should select the primary channel, and the difference between the primary and the secondary channel is minuscule. So when the primary channel becomes busy, the station waits for ifs after it's regardless of success or failure of frame reception. In turn, when the secondary channel or 2 channels at once become busy, The station waits for ifs if it successfully decodes the frame, and the ifs otherwise. And it's exactly the difference between the primary and the secondary channel in this channel bonding technique. And the station can transmit frame only in two channels at once. Okay. As for the channel bonding technique with fallback, it operates similar to the first one, but there is one difference. If station decrement the Bykov counter and transmission starts only in the secondary channel, the station may move to the primary channel, decrement the Bykov counter in the primary channel, and transmits the PPDU in this channel. After the transmission, station returns to the channel access procedure in two channels at once. Okay, now let's move to the comparison of channel bonding techniques in 11bd networks. Firstly, I would like to describe the scenario that we used in our simulation. To begin with, I will describe the Federal Communication rules of channel usage. Initially, the Federal Communication Commission has allocated 7 10 MHz channels exclusively for DSRC networks and 5 MHz delimiter. Channel 172 and 178 were used for transmissions of safety messages. So in particular region, stations separated in one of these channels. Channel 178 could be also used for transmissions of so-called wave service advertisement messages. If vehicle obtains this message, it can obtain information about services available on service channels that are purple on the slide. And they can tune to these service channels, obtain the services. Services are just some messages, and then tune to channel 172 again. Okay, and the channel 184 was used for high power infrastructure-based applications. It should be also noted that service channels, these two or these two, could be used for channel bonding techniques. However, this year, the Federal Communication Commission has relocated this band because it decided that it's underused. That's why it's retained upper 3 channels for intelligent transport systems, but unlicensed use, so in particular the Wi-Fi technology, was allowed in lower portion of the bands. That's why some real deployments have already moved to channels 180 and channel 182. That's why in our simulation we consider the operations in these channels. Okay. In our study, we consider the highway scenario where vehicles move through a 1 kilometer long highway that has 2 sides, and each side has 4 4-meter lines. 2 sides are separated from each other by 25 meters median, and speeds of vehicles are evenly distributed from 10 to 30 meters per second. There are 3 types of stations on the highway. The first type is NGV vehicles that use the 11bd standard. The second type is roadside units located on sides of the highway with a period of 100 meters. And the third type is non-NGV vehicles that use the 11p standard. And the number of NGV and non-NGV vehicles in our simulation is the same. Okay, we consider 2 primary channel selection cases. In the symmetric case, all stations have the same primary channel, channel 182. In the symmetric case, vehicles on the bottom side have primary channel 180, and vehicles on the top side have primary channel 182. The NGV vehicles transmit 2 types of traffic. The first type is cooperative perception messages that have been already mentioned. They are standardized in European Telecommunications Standards Institutes and include information from sensors like cameras, radars, lidars, and others. The size of these messages depends on the number of neighbors in the sensor's range of 150 meters. The generation rate of these messages is 10 Hz, and transmissions are broadcast. These messages are transmitted in NGV PPDUs, and channel bonding techniques are used for transmissions of these messages. The second type of traffic is basic safety messages. They are standardized in International Society of Automobile Engineers and carry information about the position, the location, about the position, the speed, the acceleration, and the size of a vehicle, of a transmitting vehicle. The generation rate of these messages is 10 Hz. Transmissions are broadcast and they are transmitted in non-NGV PPDUs. Okay, non-NGV vehicles also transmits basic safety messages. And roadside units transmit two types of messages. The first type is wave service advertisement messages. Those size is 100 bytes, and these messages are transmitted only in the symmetric case to realize this case, to allow vehicles to tune into appropriate channel. And the second type of traffic is so-called signal phasing timing and map messages that are standardized in SAE International. The transmissions are broadcast and they're transmitted in one PPDU, but the generation rate of SPAD messages is higher than that of map messages. So 10 Hz against 1 Hz. And the size of SPAD message alone is 120 bytes, whereas the size of combined SPAD and map message is 1020 bytes. So to sum up, there are 5 data streams. The first stream is a basic safety messages stream from non-NGV vehicles to all stations. The second and third streams are SPAD and map messages and VCA streams from roadside units to all vehicles. So roadside units can obtain messages of other roadside units, but they are not interested in them. The fourth stream is basic safety messages stream from NGV vehicles to all stations. And the fourth stream is the stream from, the fifth stream is the stream from NGV vehicles to other NGV vehicles, QPM messages stream. And only NGV vehicles can decode NGV frame formats, and that's why only them obtain these messages. In our study, we considered 2 quality of service metrics. The first metric is the packet loss ratio. It's computed by the following formula. So where M is the number of traffic, this PLR is for a particular vehicle, and I is number of transmission attempt, and sub M is number of attempts overall, and E sub IM is the number of stations that are expected to obtain the message I, and that are in the range of 150 meters of the transmitter and on the same highway side as the transmitter. And S sub IM is the number of stations that really obtained the message. And the second metric is frame transmission delay. That includes queue waiting time, the duration of back-off procedure, and the PDU transmission time. Okay, but to reduce the number of plots, we use the combined metric, the portion of unsatisfied stations. And we consider that the station is unsatisfied if its delay is lower than 10 milliseconds and the packet loss ratio is lower than 10% for cooperative perception messages, and the delay is lower than 100 milliseconds and the packet loss ratio is lower than 10% for all other messages. Okay, here I include only the results for basic safety messages and cooperative perception messages because the effects for all other messages are the same as for basic safety messages. These plots are for asymmetric case where all vehicles, all stations have the same primary channel, and the number of vehicles on two sides of the highway is the same. They show the dependency of ratio of unsatisfied vehicles on the number of vehicles on the highway, total number. Okay, and as we can see, the black curve is higher than all other curves, and the black curve is EDCA, and that means that all channel bonding techniques give prominent gains in the asymmetric case compared with EDCA, because when EDCA is used, there are no transmissions in the secondary channel, and that's why the secondary channel isn't used at all. Moreover, we can see that all channel bonding techniques show similar results in this case, because in the symmetric case, they always transmit 10 megahertz NGPDUs in 20 megahertz channel. The following figures show the results for the asymmetric and symmetric case in the situation where the number of vehicles on two sides of the highway is the same. I included only one plot for the asymmetric case because all channel bonding techniques, as we could see from the last slide, show similar results in this case. And the results are better than that of EDCA. So it's the best curve for the asymmetric case. And as we can see from the slides, the usage of symmetric channel selection can give prominent performance gains compared with asymmetric one, because the orange curve is higher than all other curves. It's because when in the symmetric case, the primary channel is overloaded. And we can also see that on the first figure, the red curve is lower than other curves. And on the second curve, it's higher than other curves for the symmetric case. The reason for it is that when the 11BD without fallback is used, all NGPDUs transmitted in 20 MHz channels, so they can interfere with frames of all other stations. And when the EDCA is used, NGPDUs transmitted in 10 MHz channels, and they cannot interfere with frames of stations in the adjacent channel. Okay, it's the reason. And the last effect is that yellow and green curves are very close to each other, which means that channel bonding techniques from 11A with different interframe spaces on the secondary channel show similar results. The reason for it is that the difference between these interframe spaces is small compared with the frame transmission time. Okay, now let's move to the next slides, and here symmetric and asymmetric cases compared in a situation where the number of vehicles on the top side is 3 times higher than on the bottom side. And here the percentage of unsatisfied vehicles is shown only for the top side because it's almost always higher on the top side because it's overloaded. Similar to the last two plots, we can observe that channel bonding techniques from 11A show similar results, and symmetric channel selection provides much higher performance than asymmetric one, because the orange curve is higher than all other curves for channel bonding techniques in symmetric case. However, in contrast to the last two figures, here the 11BD without fallback provides the lowest portion of unsatisfied stations for all types of traffic. The reason for it is that 20 MHz transmissions are more fruitful for stations in the congested side, and that's why the performance growth. Okay, and the last two figures show the results for the same case as on the last slide, but here stations on the top side use the 11BD without fallback, and stations on the bottom side use EDCA. I'm sorry, they used the channel access method that is varied. And as we can see, the black curve is lower than all other curves, which means that the most fruitful combination is 11bd without fallback on the top side and ADCA in the bottom side. So to sum up, we can draw the following conclusion from the numerical results. Firstly, the symmetric channel selection provides noticeably higher performance than asymmetric one. Moreover, channel bonding techniques from 11A with PIFs and AIFs in the secondary channel show similar results. Moreover, we can provide the recommendation for selecting the most suitable channel bonding technique. If in the symmetric case, when the number of vehicles on one highway side is much higher than on the other side, vehicles on the congested side should select 11bd without fallback, whereas vehicles on the less congested side shall select ADCA. In all other cases, vehicles shall always select 11bd without fallback, and they can make a decision based on, for instance, channel busy ratio. Okay, that's all for today. Thank you for your attention. If you have any questions, you can ask them. And I see one question from Vyacheslav. You compare different channel bonding techniques using unsatisfied vehicles ratio, which depends on both delay and the packet loss ratio. Which of the components, delay or the packet loss ratio, has more impact on the results for different types of traffic and cases? Okay, overall, the packet loss ratio has the highest impact on the results. So because first, the requirement for all messages apart from QPM, the delay requirement is quite moderate and it's easily satisfied. That's why for all messages apart from QPMs, the satisfied vehicles ratio is determined exclusively by packet loss ratio. But as for comparative perception messages, it's determined by both metrics, but primarily by the packet loss ratio. Okay.
Viktor, can I ask you a question?
Yeah, sure.
So my question is related more to the first part of your presentation, maybe about the standard as a whole. So you said that the channels are located in the 5.9 gigahertz band, right?
Yeah.
And that is like even higher frequency than 5 gigahertz. And we know from some experience, from some user experience, that 5 gigahertz experiences bad connection when devices are far apart from each other, especially if there is a lot of obstacles between the transmitter and the receiver. So basically, the question is the frequency of 5.9 gigahertz band enough for uninterrupted communication between two vehicles, even in cases when there are obstacles between them?
Yes, they're enough, and the real experiments say that in the transmission range, the transmission range is up to 1,000 meters are achieved, but it's naturally when there are no obstacles. But as you know, even in case of obstacles, these communications are possible, and there are some real deployments that, and there are some test beds that's shown that yeah, it's really possible. I saw some articles that provided such experiments.
Okay, maybe you know the transmission power that transmitters usually use, because 5.9 gigahertz and 1 kilometer of range sounds unfamiliar to me.
Okay, I can't recall the power that used in the study that's shown that 1 kilometer range can be achieved, but usually 23 dBMs transmission power is used for V2X networks.
Okay, I see. I think that I will look it up for some more information, but thank you for the first insights.
Thank you for your question. My pleasure.
So I guess that's all for today. Let's thank Viktor for his interesting talk. I want to also thank all the participants of the seminar for joining our seminar and asking questions. And see you. Goodbye.
Thank you. Thank you. Goodbye.